So I'm going to talk about how we do fault detection and isolation in Facebook networks at big scale. So this talk is going to consist of 4 sections. The first is kind of traditional network monitoring, which is, I suspect, how most of you started monitoring your networks and probably how you continue to monitor your networks. Then I'm going to talk about what Facebook's data center networks actually look like and how they're architected and why that presents difficulties for us. Then we're going to talk about NetNORAD, which was our first kind of active monitoring system inside of Facebook. By active monitoring, I've seen a monitoring system where we generate artificial traffic and measure it. And then more recently, since the start of this year, we've been working on a project called NFI, which started as a bit of an in-joke that we had certain classes of failures that we had no fucking idea what was going on. So we came up with the idea of, well, network fault isolation is a nice acronym we could use for this project, which is the thing that would help us figure out what was going on when we had no idea what was going on. So, traditional network monitoring. So, most of you know, if you're in a situation or in a company that has no network monitoring, it's a pretty horrible deal because the only way you find out about outages is when customers tell you that the network is broken. And ultimately, this is bad because you look like you don't know what you're doing. What's really bad is customers pretty quickly go to telling you when they think the network is broken, which basically means anytime anyone changes anything at all, software, hardware, anything else, and it doesn't work, they go, hey, the network's broken again, guys. And you go, well, we have no data to prove that it isn't. So we end up having to investigate everything manually all the time. And in a small network, this is painful. In a big network, you actually need an army of network engineers doing this all the time, and it just makes no sense. It doesn't scale. So what most people do, well, when you're debugging these issues, as most of you guys know, there's a bunch of standard text tools you use, you know, ping, traceroute, MTR, or whatever your favorite thing is. What you're trying to do is find where packets are going missing. Again, this isn't a lot of fun. It can be for a really interesting obscure problem, but most of the time it is a pretty standard thing you've come up against before. So what most people do then is like, well, turns out we need to graph stuff because basically most network outages, the majority fall into 2 categories. The first is we ran out of capacity somewhere and that was really bad, and the other is we had errors on some device or interfaces and it was dropping packets, and that's why the network broke. So you start graphing, you start using SNMP to pull out your counters, and I'm going to apologize to the Cisco people because I'm going to pick on them just a little bit, as most of the other vendors during this talk, because very quickly you realize that there's a bunch of things you don't get out of the standard counters, and you end up doing some horrible screen scraping to get some low-level counters out of your box to figure out the other class of errors that you haven't found yet. Then you build some lovely dashboards, and you have people who watch the dashboards, and that's all great, and then your network gets bigger, which means you need bigger and bigger and bigger dashboards. And this is cool, except for one thing, and this is the bit that we really kind of like. You will find through digging in dashboards most of the problems, but there's one fundamental flaw with all of this monitoring that we found, and it really starts to appear at scale, is that ultimately you're depending on the hardware and the software on that hardware to tell you that it's not working. You're polling these devices and saying, like, basically, are you okay? And the device is saying, yes, I'm fine, or it's saying, no, I'm not. But once again, you're trusting the vendors, which you shouldn't really trust anyone with this kind of information. You're trusting the devices to tell you that they're operating properly, or that they're dropping packets, or that they're out of capacity, or whatever. And sometimes they lie. You just can't trust them. You can't trust a device that potentially has a hardware or software fault to tell you accurately, or tell you, like, I'm actually fine. And then people go, well, you build your own hardware now. Surely this isn't a problem anymore. Well, kind of is. If you build your own stuff, you realize that your software, certainly starting out, is equally shitty, if not worse, than what the vendor's been giving you for the last few years. And also the hardware you're using is most likely the same kind of ASICs that they're using if you're in the commodity space, and they have SDKs, and once again, there's bugs there as well. Like, nobody writes software that works perfectly all the time. It just doesn't happen. So now we're going to need to introduce, to kind of explain what we've done, we need to introduce what Facebook's data center networks look like. So what we use is what we call our fabric networks. They're basically big cloths or cloth fabrics, depending on how you want to pronounce it. This is a wonderfully pretty diagram of what they look like. I'm not going to try and explain anything with this diagram because it's just too big, but basically you get the idea. It's a ton of relatively cheap commodity network devices and an absolute assload of cables connecting them together. So for the purposes of this talk, I'm going to go through a diagram that looks like this. So basically, the idea is we have 2 data centers here, one on the left, one on the right. We have a host. Hosts in racks are connected to rack switches. Rack switches in our network are typically connected to 4 cluster switches, which are called CSWs here. Cluster switches are connected to spine switches, once again in a full mesh. And we have inter-data center switches, where we bridge one data center to the next. Well, not bridge, route one data center to the next. I shouldn't say that in front of a networking audience. We have spine switches in data center 2, cluster switch in data center 2, another rack switch, another host. So this is basically what it looks like at a very small scale. We have, once again, a bunch of commodity devices, a bunch of links. ECMP is the thing we absolutely rely on to make these network works. And obviously, I probably don't need to explain this. I'll go through this quickly because most of you know what this means. But basically, you want to send traffic from host 1 to host 2 here. Send it to the rack switch. It's your default gateway. It's the only place you can send it. He then has 4 choices of where he can send this packet. This is where it gets interesting. Obviously, that decision is typically made by hashing these 5 fields on the TCP IP header. You take the protocol, in this case usually TCP, source address, destination address, source port, and destination port. You hash them, and that's what you choose which of those 4 interfaces is going to do. Send traffic on. And once again, this continues layer by layer in the network. But this means a couple of important things, and it's been designed like this for very good reasons. Firstly, in a single TCP connection, all of the packets should take the same path. And the idea is, or the optimization here is that, firstly, it's faster to be able to hash these things and send them. It also means the end hosts on either end shouldn't get out of order packets because the path is the same for that TCP connection. It also means that packets for different TCP connections are going to take completely different paths through this network. And most people don't realize that. So what happens a lot is like something's broken in one of our networks and someone sends us a trace route and we're like, oh great, you've shown us like 5 of the links that this packet could have passed, even though we have no idea where it actually went. So we kind of said, well, this is kind of a bad deal. We need to fix this. So we decided to write our own traceroute tool called FBTraceRT. The idea of FBTraceRT is, well, we send traceroute requests from a huge number of source ports. So it's actually configurable on the command line. Typically, we use hundreds to try and enumerate our networks. Again, how traceroute works is we send a bunch of packets with a TTL of 1 from different source ports. I said there's only 4 illustrated here. Typically, there's actually hundreds of these. The rack switch is going to reply to all of these saying, hey, TTL is 1, TTL expired, here's your ICMP message. Again, next send packets with TTL of 2. They're going to hash differently based on the hashing algorithm because the source ports are different, so they're going to go to different devices. Those devices are going to reply, and so on. But ultimately, what we can do with FBTraceRoute is basically figure out what the entire topology between 2 hosts is, even when there's hundreds, if not thousands, of individual links in between them. So this obviously means we can figure out what our network looks like and all of the links that we're possibly touching between 2 hosts. That's nice. So NetNORAD, the idea of NetNORAD is we had all of these classes of problems where we said, well, we really need to measure what our network is doing for our customers. So we can't just assume that looking at all these counters, it's going to tell us it's okay. And there's one other thing that I like to point out, particularly to the network audience, is that latency is generally not given to you in any counter. When you're buffering packets, which a lot of big network devices have pretty big buffers, inside our data centers, you can do a small request in like 1 millisecond. A network device or a chain of network devices between them might have 70, 80, 100 milliseconds worth of buffering in them. Customers will notice that really quickly in their service metrics. They go, oh, look, like my request used to take 10 milliseconds and now they're taking 100. What the hell? And what you can figure out pretty quickly is if your network gets congested and you start buffering packets at a few layers, that suddenly you're introducing a whole bunch of latency. And pretty much, like very few network vendors will actually give you this is how full my buffer is, this is the amount of actual extra latency I'm adding to each packet as it goes through. So one of the ways we try to find this, well, why don't we just send a lot of traffic? So the idea of NetNORAD is basically we have a bunch of designated pingers in the network, ideally distributed all around the place, and they're going to send pings to basically responders on every host. So ideally every host, realistically we try and get a few hosts in every single rack at Facebook. So we're trying to ping basically the world from a subset of hosts and measure latency and loss. So it started out, as most things do, really, really simply. It was a Python script that ran ping on the command line, collected the output, and started to process it. Obviously, that didn't scale very well. Then we started sending TCP, so we started using raw sockets and sending TCP, just individual TCP packets, and relying on the reset to give us our timing and reachability information. This worked really, really well until people started complaining a lot inside of Facebook because people monitor the TCP reset counters on all of their hosts, and suddenly they started to go up a lot, and they're like, holy crap, something's gone wrong here. So we said, okay, so we started using ICMP probing. This actually, we didn't use it for very long because we had the problem of ICMP doesn't have source ports, so we weren't necessarily sending traffic, we weren't doing hashing very well over the network, so therefore we didn't have a good idea if we're actually enumerating all links properly. So ultimately, we ended up using a UDP probe. So we have a little UDP agent that sits on basically every single host at Facebook, and then we have these pingers that send literally millions of packets per second. The UDP probe format is really simple. There's a signature, which is basically just a unique identifier, so we can tell the response. Obviously, timing information, send time, receive time, response time. We also do a lot of QoS on our backbone network, so therefore we have different QoS tags on different packets, so we can basically test all of our network, or all of our virtual networks, if you want to look at it that way, to make sure they're all performing well. So we open source the UDP pinger as well. This is something we think other people might find useful, so you can send literally a shit ton of UDP packets around the place and the responder. They're quite simple. Well, Requester is quite complicated because it'll be heavily multi-threaded and it's optimized for very high performance. The responder is literally just a tiny little UDP daemon that responds back to these things and adds some timing information. So what do we actually do with all this data? As you can imagine, in a network as large as ours, and unfortunately I can't tell you how many hosts or network devices it is, but there's a shit ton, which means it generates a shit ton of data. And what we really care about, we don't care about if individual hosts are up. Well, we kind of care, but we don't really. Like individual hosts or individual responders not responding isn't a big deal for us. That doesn't tell us the network is broken. What we want to understand is if a cluster, or racks and clusters are really the unit that we're interested in. So a rack is obviously a rack of servers with a rack switch in the top, and a cluster is a bunch of racks that are connected to the same level of the same aggregation layer, the same set of CSWs. Really, we just want to care, is this okay, or is this broken? Is it not performing as we'd like it to? So we need to talk a little bit about the hierarchy of Facebook networks. So we have Backbone, which basically connects everything together. We have different data center sites, of which there's 5 or 6 now around the world. For most in the US, is actually building one in Dublin right now, which is kind of nice for us. On a site, we typically have more than one building, so we tend to build mega data centers. We buy a big chunk of land and we put a couple of buildings on it. Inside the buildings are bunches of racks, or what we call clusters, and clusters are composed of individual racks of servers. So in the US, we have obviously multiple sites, which are architected the same way in terms of network hierarchy. We also have little pops dotted all over the place where we try and do image caching and SSL termination, obviously make things faster for the customers. What we figured out with NetNORAD is, first thing we need to do is basically understand the health of all the racks. So inside a cluster, we have ideally 2 dedicated pinger boxes, so we try and get those out of the provisioning people who give us hosts. We say we need 2 pingers in every cluster, and we're going to ping every single target that we can inside that cluster. So make sure that we get at least 2 or 3 in every rack, and do a very, very aggressive pinging inside the cluster. But that's really only covering the very bottom aggregation layer of the network. So then we said, well, how can we look at getting more data? So we said, well, inside the same data center, if we ping from a different cluster, that gives us one bit of information. If we go from a different data center in the same region, we ping that cluster. And also we go from a completely different region, we send traffic into this cluster. And this gives us 3 different views of information. But what this is really nice for is that when we have an issue, so let's say local cluster inside the same data center, everything's fine. But from a different data center in the same region, we start seeing packet loss. And then from a remote site, we start seeing packet loss. Actually, we can try to triangulate, well, basically, this obviously is an issue in this data center because nobody else is seeing it. But also, it's probably actually at the spine layer of this data center because that's where the traffic is going to go to get to these other places. So this is what we've used for about 3 or 4 years now. NetNORAD has been evolving. And it's been very effective in us understanding how well our network is performing for our customers. But there's a problem. And particularly as we started rolling out our commodity networks, we realized what this problem was. So NetNORAD will tell us that something is broken, but what we want is our alarming to be as accurate as possible. So NetNORAD alarming is accurate. It tells us when there's problems. It doesn't tell us exactly where it is, and therefore we can't auto-remediate based on it. We can basically say, people in this cluster can't, or hosts in this cluster can't ping hosts in this other cluster. Please go investigate human being because I have no idea of what's actually happening in the middle. So this is the problem. These big fabric networks, as they rolled in, what actually happens here on these diagrams, if we examine there's hosts at the bottom and hosts at the top, NetNORAD will tell us that they can't talk to each other. It could be any one of those links or devices in the middle that is actually the root cause. And it's going to impact a very small subset of traffic, but it's going to be a very real set of traffic. So we decided to think, well, how can we actually approach this problem in an automated way? Because we can't have people doing this work manually all the time. So we went back. Really what we would find is the kind of hard cases for us is the box in the middle of the network, something that's 3 or 4 layers deep into the network. It's not close to any server. How do we find out that this box is the one dropping packets as opposed to one of the others? Or even an individual link between 2 devices a few layers deep into the network. How do we find it? So first thing we said, well, we have all of the code that does FB traceroute. We can do very aggressive traceroutes, which means we can map the topology. So what we started doing from these hosts, we dedicated hosts. We wrote a new agent called NFI, both a client and a server agent. And the first thing it does is a whole ton of TCP traceroutes. It literally takes thousands of source ports to enumerate the networks. Unfortunately, our networks are very large and have lots of links in them. So we do lots of it, and therefore, we discover from all of these source ports where this traffic is going to go. And basically, we build a table. This table maps for us, if I send traffic from TCP source port 50,000 to destination port 9999 from these 2 hosts, these are the links I'm going to touch. And we build this table. Once again, it's typically several thousand entries deep. And then this is where the interesting part is. We start sending thrift requests. So thrift requests are little TCP requests, and we use them basically for all inter-service communication side of Facebook is using thrift. But you can think of them, they're basically like little HTTP requests, although a little bit faster. So we send lots of these thrift requests. The important part is for every thrift request, we actually set the source port, which is obviously not something you do most of the time, but we actually send a request from port 50,000, port 50,001, port 50,002, and so on. And we cycle through these as fast as we can. We try and do at least a couple of hundred requests a second from source to destination. Again, obviously because of the hashing, by sending a request with the same TCP, obviously TCP request, we do TCP trace routes, same source address, same destination address, same source port, same destination port. What we discover is when we drop a packet, so we do a request from, say, port 50,005, if that packet drops, we can infer, based on the trace route we did a minute or two ago, that this is the path it took through the network. So if we drop another request, once again, it's going to take a different path, but we'll know what that path is. And then the interesting bit is when we look at this in aggregate, so every minute we aggregate the data from each host that's generating this data, and we look at all the requests that dropped and all of the links that those requests touched. And then naively, I thought, well, this is easy. We just graph it, right? Anytime we see a link get hit more than once, we increment the counter for it, and we create a graph. And then we started doing this, and it totally didn't work. And I ended up with graphs that looked like this. And I was like, okay, there's not really a lot of good signal inside here. I mean, this could be the first device or the spine switch device in the middle here. And then I said, well, there's more in this data here. I was convinced there was more in the data, and I had to bash my head out of the table a few times to figure out what I was missing. And what I was missing was actually something quite simple. The number of links between each layer in the network was actually the most important thing. And because it's all about statistics, right? This first link here that was hit twice from the rack switch to the CSW, there's only 4 links there. Hitting that twice is not that statistically unlikely. The link here that I hit twice, there's 48 different links between those 2 layers in the network. Therefore, statistically hitting that twice is much, much lower. So therefore, when we factored in the size of the width of the network between layers of where we saw stuff, suddenly our graphs got a lot more detailed and gave us a lot more signal. So even in like losing 2 requests here, statistically speaking, that spine switch link is much more likely to be the root cause of a problem here than the switch or the switch CSW link at the start. So this all sounds a little bit academic right now, and it certainly was to begin with. One day I came into work and I saw a graph like this, which we'd produced overnight, and I was like, this looks bad. So I poked the network engineer. I'm not a network engineer, obviously. I poked the network engineer behind me and said, hey, Jose, what the hell's going on here? And he's like, I don't know. He looked at all the graphs for this device. Everything looked fine. Logged into the command line, ran every command that he knew. Everything looked fine. And then we said, well, it's one device of many. Let's just take it out of service. And suddenly we took it out of service, and this loss went away. Then I actually pushed a new version of software because I've written enough code to know that this shit never works the first time. So rolled a new version, and we brought the device back into service, and again, it implicated this device again. Took it out, and rolled it in. So this is what those 2 drops are, and then we took it out of service. We went back to the vendor, which I'll point out wasn't Cisco in this case, and said, hey, what the hell? Like, this device says it's okay, and like it's dropping packets, or we think it's dropping packets, and it wasn't dropping a lot. We're talking a fraction of 1% of packets, but it's still material inside Facebook's network. And eventually they came back and said, oh yes, you have to run some command line things. There's like 50 million counters inside this ASIC. You run this command for each one of them. And we said, like, there's no way we could ever do that feasibly on all of our devices. You have to come back with something better. But it was the first time we found what we call a gray failure inside of our network, a device where we had no idea it was dropping packets. It certainly wasn't reporting by any counter that was easily exposed to us that it was dropping packets, but it actually was broken. So that all sounds awesome. We've solved the world's problems inside of Facebook, at least. Except we kind of hadn't yet. This was really, at the start when we did this, this was really a pretty decent prototype, but not actually a full service. So first thing we said is, well, we want this to be pretty modular. So we architected the code a little bit. There's basically 2 components of it. There's a client and the server. The server is really easy. So it's a thrift server, which is basically, you can consider a little HTTP server. You send it requests, it sends direct responses. It does exactly like the UDP server for NetNORAD. Basically, it just adds timing information and reflects the packet back at you. The client is where all the real work happens. So the client's its main thing is to aggregate all the data it collects and push it up into our stats system so we can actually look at it all together. The 2 main components of the client are, there's the NFI requester and what we call the topology discovery. So the topology discovery is using ztrace, which is basically a C program we use to do the very efficient trace routing by sending lots of packets from lots of source ports. And then we have a thrift requester. And all of this was written in Python. Ztrace is something we could use inside of Facebook because it was a foundational component, so it was already written in C for FP tracers. And then we decided, one of the things we found out is that we really wanted to find very low levels of loss, and we just weren't doing enough requests. So we decided, well, what if we rewrite some of the key components in C++? So the thrift request, that's the thing we send at very high velocity. So we said, well, we'll rewrite that in C++, and we'll rewrite the requester in C++, the server and the client rewritten in C++. It turns out that like writing stuff in C++ makes it way faster than when it was written in Python. So these are latency graphs that we had. So like at our P99 levels, we were seeing latency from one data center to another of like 7 milliseconds in kind of our worst cases. And this suddenly went down to 1 millisecond when we rewrote the server and deployed it. We wrote the client, again it dropped. We also increased the request counts, the number of requests we were doing, by 4x when we rolled out the client, which meant we were getting 4 times as much data in a minute, and it was way more consistent, which obviously means we can detect, because ultimately what we're trying to do is find the lowest level of packet loss that we can. So the next problem we had was traceroute is unidirectional. So we kind of glossed over this right at the start. We're like, well, we're going to do all these thrift requests from source to destination, and we're going to do traceroutes from source to destination. But that reply traffic is going to take a completely different path back to us, and we're just going to kind of blindly ignore that and say, well, the signal we get on the outgoing path will probably be good enough. And it was, but once again, we had a lot of noise in the data. So we said, well, what can we do here? So we said, well, we have all the components. What if we did reverse traceroutes? What if we used the same command and actually did reverse traceroutes? So now what the client does is when it starts sending requests to the thrift server, it sends a special thrift that says, like, hey, start doing traceroutes back to me. Here's the range of source ports I'll be sending you traffic from. So you use that as your ports when you send the traceroute request back to me, and then I can request at a regular interval, and you can tell me how all of these packets are going to route back. So we just started running ztrace on the server back to the client, and then the client can request this data, which means when we're doing data aggregation on the client, it knows not only the outbound path for all the packets, but also the reply path that they should have taken through the network. So what's next for NFI? So we haven't solved the world yet. Thing that's big for me, and actually when I gave this talk a week ago, it was running on Wedge. We have our own switches. Our switches have a pretty decent CPU in them. They actually behave like a Linux box. So we're like, well, if we can run agents on these, we can get coverage of basically the entire network because these rack switches are everywhere. Right now, we're dependent on actually getting hosts in all of the clusters to get complete coverage. And as of last week, when I last gave this talk, we'd never done this. On last Friday, I got it up and running on a development version of code for this. So I'm very excited that this will kind of complete our coverage woes of all the places in the network that we can't cover. And the kind of elephant in the room for us is we have this wonderful backbone network, which is all MPLS. And as you nerds probably know, traceroute works really well in IP networks, not so well in MPLS networks, and that's kind of the underpinning of how we discover topology. So this is the bit we're working on right now, is basically how can we discover the topology? That's why we tried to make the code a little bit more segmented. So we want to be able to discover the MPLS topology and the LSP topology in order to understand when we're sending traffic between sites, because right now we can triangulate into the data center. We can't triangulate between different sites, between different regions or in and out of the POPs. So why does this all actually matter? You kind of think, well, you've got one device of like hundreds that's dropping a few packets. Distributed systems hate packet loss, and distributed systems hate packet loss because TCP is designed to view packet loss as the network is full. So therefore, whenever TCP sees packet loss, it goes, hey, the network is full, I'd better slow the hell down. So this absolutely destroys your throughput inside a network, and obviously increases your latency. The other big problem is the 200 milliseconds min RTO that most people are familiar with if they've looked at enough graphs. Anytime you drop a packet, you wait 200 milliseconds. It takes 1 millisecond to do a request, one of these small thrift requests in our data centers, 200 times X if you drop any single packet in there. So it becomes a big deal. The other thing is because of the hashing. Let's say you have two databases that are replicating from two different sites. Depending on the source number of the TCP connection means how you're going to hash through the network. So one of them can be performing fine and one of them can be performing terribly because it happens to be routing across a bad link. You know, go to your average systems engineer or application developer and say, like, oh, why is one of my database replications really slow and one of them's fast? Same hardware, same operating system, same code. What the hell? It's really hard for them to troubleshoot those, and understandably so. But realistically, what it's all about is us and the networking team not doing a lot of work. Because frankly, at Facebook, we'd like to think we have better things to do with our time. And we have a fully stocked bar in the Dublin office, which we like to make very good use of, particularly in the evening times. So we try to drink more and troubleshoot less. Thank you very much. Yes, questions?
Shall I wait for a mic or shall I?
Hi, I'm Dimitrios Pesaros from the University of Glasgow. Very nice talk, thanks.
I've got two interrelated questions. So you made the decision that you don't want to base your measurement on counters that your equipment runs and resort to active measurement instead. Now, the problem with active measurement is the Heisenberg effects. So my first question is, other than sort of crude fault diagnosis, do you have high confidence that the performance reported by your trace routes essentially reflects the performance of the applications that run on top of your data centers? And my and my second question is, does your measurement process is your measurement process low overhead enough so that you can afford to have it running always on rather than on demand if you want to diagnose a particular thing?
So it's always on as it is. I mean, realistically, we obviously consume a reasonable amount of hardware in doing this, but we have lots of hardware. We don't worry about that too much. The reason we actually use thrift requests for the actual measurements is because they are basically how all of the inter-process or inter-host communication happens inside of Facebook. So the traceroute is just for discovery. The actual measurements we do and the timing and loss is all based on thrift requests, which are all TCP and look exactly like regular requests in network. Because that's one thing that I was always worried about. And it's one reason I don't like the UDP probe we use in NetNORAD, because the percentage of our internal traffic that's UDP is tiny. And it's not inconceivable to have a problem where a network device will not forward UDP traffic but will forward TCP or the other way around. We also, I wouldn't say we don't use counter polling, we use that as well, but basically we understand at this point that there's some stuff that it's just not going to find because those counters aren't going to be exposed or we don't know about them yet. So we basically use this as and we combine the two data sets as well. If we see CRCs on a link, we'll obviously see this data light up as well, and it's a great way for us to figure out that if our data is accurate or not. And we obviously try and coalesce those alerts together, so we go, well, actually, this is the result of CSCs. But if we don't get that, we still get a link saying it looks like there's a problem or this link is performing substantially worse than any of its neighbors. And actually, all of the alarming is around, which actually the alarming was harder than I'd hoped, is you're basically looking for outliers. You're not looking for a particular number of high or low. You're looking for one link that's performing worse than the others. Because the problem is congestion causes packet loss in the same way that packet loss causes packet loss. So therefore, congestion looks like packet loss, and what we end up doing is triangulating to a bunch of devices in the congested part of the network. But the auto remediation for that, normally, when you see packet losses, you take a device out of service. If the packet loss is a result of congestion, taking one of your devices out of service makes that congestion worse. So that's actually the hardest part about the auto remediation part, which we haven't gotten to yet, is making sure we're super accurate in this device is an outlier compared to everybody else, and he's not struggling because the network is out of capacity in that region, and therefore by pulling a device out of service, we're going to make it worse.
Okay. Thanks very much.
When you were kind of analyzing the data and showing that the network paths made the difference to the graphs, do you have a really good machine-readable structure of your network so that you can understand how the different paths make a difference?
So interestingly, we do have a big database, and we've only actually started harnessing. We do have our whole topology in a database, and a bunch of people gave talks earlier about how to build their configs, and to me this is the hardest part that I've seen in two big organizations, is actually having some software system that can reflect your entire topology is really, really hard, and nobody has done it generically yet. Facebook has one that does Facebook's network, Amazon has one that does Amazon's network, but having a generic thing that you can describe your entire network topology is really hard. So we do have one of those at Facebook. Actually, when we started out, we've kind of said, well, traceroute is building us this map. So when we do the traceroutes, we basically get all the topology information out of it. So we also understand the number of unique links between each path, because we basically have a whole bunch of data that we can just iterate through. So we actually get it all from the traceroute data as to how many links are between each layer, and it's how many we discover. So we did actually start recently, in order to ensure we got good coverage, started analyzing the data, the traceroute data we generated with what was in the database of where the traffic should be going. Because the database is great, but that's kind of optimistic. It's this is everything that's connected to everything. That doesn't mean it's routing traffic. It may be incorrectly configured. Traceroute actually tells us what's actually going. And when we started producing the traceroute data and the number of paths, obviously, if it was a nice even multiple of 2, we were okay, we found all the paths. Because usually it was 4, 16, 48, up to 768 in some cases, which is kind of terrifying between 2 different layers. So that was kind of how we got an understanding of if we're actually enumerating all the paths properly, because obviously we don't want to have blind spots, because the worst part about network monitoring is your network monitoring says your network is totally awesome and there is packets being dropped somewhere because you have a coverage gap.
Okay, thank you, Richard.
Thank you.